addressing this group of people. So I'm going to be presenting on joint work with my friend Mike Lipnowski, who was a student of Akshay Venkatesh. So he's coming from number theory. I'm coming from more Teichmuller theory and dynamics. And Mike was until recently at McGill and just moved to Ohio State. So a fundamental question that many of us want to address is, what does a typical surface look like? In this audience, you'll be aware of all of the beautiful and deep work that studies the case where the surface is maybe the Riemann surface, or at least the genus is fixed. And you try to take a scaling limit and you compare it to very rough objects like the Brownian map or the Liouville quantum gravity. So that's a line of work that I've been appreciating from the sidelines as a non-probabilist. I think it's very stunning. Today, though, it's going to be very different. I mentioned that largely to make a contrast. Instead, today, the genus is not going to be constrained. We're thinking about high genus surfaces. And rather than a very rough metric, we have a smooth metric, actually the hyperbolic metric of constant curvature -1. And this will bring us a little bit further from some things that have been done related to things like the Brownian map, but a bit closer to subjects like Teichmuller theory and number theory. And so I just want to start with the most basic construction of hyperbolic surfaces. And so often when you talk about hyperbolic surfaces, you talk about pants, which are spheres with 3 boundary components. And actually, given any 3 positive numbers, you can build a unique pants with a hyperbolic metric, so that the 3 boundary components are geodesics of those 3 lengths. So that's one of the most important things to know about hyperbolic surfaces. And it allows us to build a lot of surfaces by gluing together pants. So for example, if you take a whole bunch of pants and you make all of their boundary lengths to be the same, you could sort of glue them together, pairing the cuffs in some arbitrary way, and in this way you get a closed surface. More generally, you just need to make sure that the lengths match up. So when you glue 2 cuffs, you're actually gluing 2 geodesics of the same length. One of the most naive observations to make is that since each pant has 3 cuffs, the gluing pattern is given by a 3 regular graph. So for any 3 regular graph, you could take a pants for each vertex, and then sort of the half edges at that vertex would correspond to the 3 cuffs, and you could glue all of the pants according to the pattern of that 3 regular graph. And the number of edges, vertices, and genus are all linear related to each other. And that's something I really want to emphasize. Is that thinking about high genus surfaces is related to thinking about 3 regular graphs with a lot of vertices and a lot of edges. And in fact, we're going to be guided by the study of typical large 3 regular graphs, or deregular. It doesn't really matter that we're taking 3 regular, but let me just stick to 3 regular for concreteness. And so there's sort of a meta conjecture or an analogy that's emerged, which is for every theorem on typical large 3 regular graphs, you should try to prove a corresponding theorem for typical high genus hyperbolic surfaces. And so some instances of this are known, many are not known. This meta conjecture may eventually break down, but for the moment, and I suspect also for the next decade, this will be a guiding principle. And so I want to emphasize that if you're comparing high genus surfaces to work in probability, it's actually best to forget about other models of random surfaces like the Brownian map that has a very different flavor. The closest analogy is really random regular graphs. And so one of the things, so I should say, usually when I give this talk, I am not addressing an audience of probabilists, and I spend a bunch of time talking about what does a random three regular graph look like and what are the basic results. And I made the decision to skip most of that today in favor of sort of emphasizing what's similar and what's different when you study random surfaces, random high genus surfaces versus random three regular graphs. And absolutely the first difference that you instantly can't avoid, if you're interested in, say, genus G hyperbolic surfaces, well, you instantly run into the fact that the set of genus G hyperbolic surfaces is infinite. In contrast, if you looked at the number of three regular graphs on a fixed number of vertices, that's finite. But you should make the comparison. On the one hand, you have what I would call the moduli space of hyperbolic surfaces on genus G, and on the other hand, you have the moduli space, or just the set of regular graphs on, say, a fixed number of vertices. And anyways, given that this set is infinite and it's not even discrete, it's a high dimensional manifold, you face the instant question of how to define a random element. And there are really, substantively different ideas about how to do that, and I'll talk a little bit about that. And so the most naive model, if you want to really connect to three regular graphs, is maybe you fix some cuff length little l and take a bunch of pants of exactly that cuff length, and you glue them together according to the pattern of a uniformly chosen random three regular graph. And you can do that. It's not a popular model because there's not a lot that can be said beyond the obvious that you can make a coarse comparison to a three regular graph. But you could do that. That's probably the most obvious thing. Then maybe the next most obvious thing is to glue together random triangles. And again, I want to emphasize here that the genus is not constrained, so the number of triangles would be proportional to the genus. So this is very different for situations like the Brownian map. Anyways, in my world, this is called the Brooks makeover model. So you use a random three regular graph as a guide to gluing together triangles. And quite a lot of work has been done on that. And then there's the random cover model, where you fix maybe a genus 2 hyperbolic surface, and you say, look at all of the degree D covers for some big number D. That's a finite set, and you pick one uniformly at random. And a lot of beautiful work has been done there. So one thing to emphasize, though, or to realize, is that all of these models do use a uniform measure on a finite set. So for example, if you pick a base surface and look at degree D covers, there's finitely many. And I think that's what led people to them is if you're looking for a random model, it's natural to restrict your attention to a finite set of surfaces and then pick uniformly from them. But the downside is that these models see only finitely many points in this huge 6G minus 6-dimensional manifold of genus G hyperbolic surfaces. And so really, they miss a lot of them. So really, they miss a lot of this moduli space. And I would say that they're sort of trying to, in some sense, avoid the surface geometry by reducing to a discrete problem rather than really embracing the surface geometry. So anyways, alternately, you might ask if there's some sort of natural measure, probability measure, whose support is the whole moduli space. And there is a stunningly beautiful measure. So the answer is yes, and there's a measure that satisfies far more properties than you even have the right to ever hope for. And it's called the Weil-Petersen measure. And so this is a finite measure, fully supported on the whole moduli space of genus G Riemann surfaces. And its study in the context of random surfaces was pioneered by Mirzakhani. She devoted her ICM talk to Weil-Peterson random surfaces. Before that, to my knowledge, they weren't studied because she hadn't yet built the tools to study them. And anyways, I want to tell you a little bit about this measure to give you an idea of its really stunning naturality. As I said, beyond what anybody could ever expect. So it's based on what are called the Fenchel-Nielsen local coordinates for the moduli space of hyperbolic surfaces MG. And I just want to outline those coordinates to you very briefly. So I want you to think about starting with a fixed surface X and consider a Pants decomposition, which you can think of just as a collection of 3G-3 disjoint simple geodesics. So this is a maximal collection of disjoint simple geodesics on the surface, and they cut the surface up into Pants, which is why you call it a Pants decomposition. And so if you want to find local coordinates near X, your starting point would be to just consider the lengths of these geodesics and how they vary as you vary the hyperbolic structure. And so the lengths of these 3G-3 cuffs give what are called the 3G-3 length coordinates. And then there are also 3G-3 twist coordinates that keep track when you glue two pants of how they're twisted relative to each other. So it's a little subtle actually how to define twist. What's much easier to understand is how to define changing the twist. And so here I've drawn a picture of how to think about the twist at this red geodesic. And so if you want to change the twist, you should cut the red geodesic and then just re-glue it by a different isometry from the circle to the circle. And that changes the twist. So anyways, in total, you have these 3G-3 length coordinates and these 3G-3 twists. You could think of them as complete instructions for building your surface out of Pants. You start with Pants with the right cuff lengths, and then you glue them with a certain twist. And in total, they give 6G-6 local coordinates for the moduli space of hyperbolic surfaces. Are there any questions so far?
Not at the moment.
Okay.
Yeah.
Oh, there's a question.
So about your previous point, surely the discrete surfaces you mentioned are capture all of it in some other sense, right? Perhaps they're dense if you look at all of them together.
No. You know, for example, if you use covers of a fixed surface, they retain a lot of the geometry of the bottom surface. So for example, if the bottom surface doesn't have a short geodesic, neither will any of its covers.
And the other two models?
So people frequently claim that the Brooks makeover model sees all of MG. In my mind, that claim is severely misleading. You do see all of MG if you sort of fix the genus and look at bigger and bigger triangulations. You'll get a dense subset of MG, and you might even, that's very meaningful, but that's more of a Brownian map or Liouville quantum gravity sort of thing when you fix the genus. If you're not constraining the genus, then you're, the best you can sort of expect for is coarse, like some very coarse form of density.
It might be worth mentioning that I think there's a student of Larry Goots, Shahana, I'm blanking on her last name right now, who just did some, sorry?
Vasudevan?
Yeah, Vasudevan, that's right, who just gave some quantitative version of this, of the density that you're mentioning.
But it's coarse density.
It's very coarse, very, very coarse. That's right, that's right.
Yeah, this moduli space is infinite diameter in most metrics, so you can't really expect a finite set of points to really see all of it.
I see. Thank you.
Yeah, no, that's a great question, though. Okay, anyway, so where we left off is we have these 3G-3 lengths, and then that sort of say which pants we're using, and then the the twist coordinates, which say how to glue them together. And that's like sort of a complete set of instructions for assembling your hyperbolic surface. And these twist and length coordinates give local coordinates for the moduli space, called local Fenchel-Nielsen coordinates. One problem though is that each point, so each hyperbolic surface has infinitely many Pants decompositions. So it's contained in infinitely many local coordinate charts, and they're all sort of equally natural. And there's a fact that's so magical that it's usually called the magic fact or the magic formula, even by experts in the field, due to Wolpert, that says that the standard volume form in these coordinates doesn't depend on which local coordinate system you use. So if you start in one Fenchel-Nielsen local coordinate system and you write down the standard volume form, and then you switch to another a local coordinate system, the formula for the change of the coordinates can be heinously complicated, but the determinant is one. Although it's not usually proven directly because the formulas would be so hairy. In fact, there's a lot of deeper geometry underlying this, which is how it was discovered. Anyway, so we have this very natural Lebesgue measure. It's this sort of miraculous situation where we have infinitely many local coordinate charts, but the standard Lebesgue measure in all of them agrees with each other. And that's actually a finite probability measure called the Weil-Petersen measure. And that's what I want to focus on today. Before I get into too much, really diving into the Weil-Petersen model, though, I do want to say that we are in a good situation. You do have different groups of people looking at the same questions in different models for high genus random surfaces. Thankfully, the answers tend to be the same independent of the model. Maybe
I have a question.
Different. Yeah.
So you mentioned that this the big measure is a finite measure. So why this is finite?
That's not obvious. Maybe I can tell you afterwards.
Okay.
The key thing to know is that there's some number depending only on G. So every genus G hyperbolic surface has a Pants decomposition where all of the Pants are length at most that number.
Oh, I see.
So that's the so-called finiteness of the Beer's constant.
Okay, I see.
And if you know that, it's sort of an exercise to show finiteness. And if you don't know that, it would be completely.
Oh, I see. Okay. Yes.
Yeah, I see some chats. I'm just going to quickly. Oh, thanks, Jaida, for putting Sahana's paper on the chat. Okay, anyway, so we're in a good model. We don't have to really argue too much about which model. They're at least sort of giving the same answers. So we don't have anything like any contiguity results. That would be just amazing. There's no a priori reason we know of why these different models give the same answers, but they keep giving the same answers. So they all seem to be seeing the same, Platonic truth for what a random surface should look like, even though they are, really a priori different models. Anyways, I hope to really show you, though, that there are some advantages to the Weil-Petersen model. So the Weil-Petersen model is just when you pick uniformly at random according to this Lebesgue measure in local Fenchel-Nielsen coordinates. It really has some advantages in naturality and beautiful statements. And I just want to show you one statement that maybe reflects some of the beauty of this model. And so for this, we're going to look at a random variable on the moduli space of genus G surfaces called NAB, which will be a natural number valued random variable that denotes the number of primitive geodesics of length in this interval AB for a Weil-Petersen random surface of genus G. So this is an integer valued random variable. And the recent theorem of Mirzakhani and Petri is that these random variables are Poisson. And they're Poisson with a beautiful mean that's just given by this integral of e to the t plus e to the minus t minus 2 over 2t. And so, you'd expect something along these lines for the other models. It would not be as beautiful to formulate because none of the other models have quite the same naturality. If you have a finite set, it's sort of hard to get these smooth distributions for questions like this. So one reason I wanted to show you this theorem was because I think it illustrates the beauty of the model. The other is just because this is a very special theorem for me because it's how I got into this business. There are many, many ways to be sucked in to the spectral geometry of high genus surfaces. And you might have different groups who had different, primary motivations. But for me, the starting point was this theorem of Mirzakhani and Petri. And the work I'm going to talk about on it, I view as a generalization, as an extension of their work. Even though, as I said, there are many ways to get to the same point of being interested in the sort of questions I've been interested in. I should say this is an extremely beautiful paper. If any of you are looking for a paper to read that will get you interested in this, it's not too long. It illustrates all of the key ideas, and it's very nice. So one thing I want to notice is that there's no G in here, and this function that's being integrated has full support all the way down to 0. So I just want to note in particular that as has to be the case for any model whose support is the whole moduli space, there's a positive probability of a hyperbolic surface having a geodesic loop of length at most epsilon. And in this case, it's about epsilon squared and roughly independent of genus. So you really do have some definite chance of seeing a very, very, very short loop on your surface. And if you're comparing to random graphs, in a random graph, all the edges have length 1, so you can't really see tiny loops in the same way. And this is an omnipresent added difficulty, but I would say not the key difficulty. And so I'm just going to sweep it under the rug today. Again, sort of comparing random graphs to surfaces, there's a much bigger difference. Coming back to the first difference, we have this non-discreteness of MG, the moduli space of hyperbolic surfaces, so we can't count. And so, a lot of results for graphs, you sort of literally count. There's a finite number of something and make estimates. And of course, you can't do that here. But there's only two key differences I'm going to emphasize today. One is just that MG is not discrete. And the other one, the second key difference is that the added surface geometry makes recursive arguments more beautiful and powerful. So the two key differences, the one is sort of the bad news, the moduli space is not discrete. And the second key difference is we have added geometry when you're comparing to graphs that really makes it natural to do a lot of recursive arguments in a way that, to my knowledge, is a bit different than anything that's happened for graphs. And so I just want to sort of tell you one of the key constructions. So for example, maybe you start with a surface X, so a genus G hyperbolic surface, and you take gamma, a closed geodesic of length L, and you just cut it. So when you cut it with scissors, it becomes 2 closed geodesics. And in the typical case, you've reduced the genus by 1. And so the result of cutting this geodesic is this surface X minus gamma that has genus 1 less, and it has 2 boundary components, and both of the boundary components have length L, where L was the length of gamma. So what you do is you get a surface X minus gamma that lies in this smaller moduli space of genus G minus 1 surfaces with 2 geodesic boundary circles of length L. And so the point here is that this moduli space, from the perspective of Teichmuller theory, is absolutely just as natural as the starting moduli space. And this is really a difference, I think. If you had a graph, you could cut out a loop and then you'd maybe have half edges I imagine you could sort of force that perspective, but it doesn't seem as natural. So really, this sort of construction that I just illustrated has the like central role in powering recursions, and those recursions are the central tool in the field. So using this sort of idea where you cut a simple geodesic, one that doesn't intersect itself, you get complicated but beautiful recursions for the volume of the moduli spaces, which Mirzakhani used to give a new proof of Witten's conjecture, and you could get formulas for integrating certain special functions over the moduli spaces. And again, I just want to emphasize, when I say integrating a function over a moduli space, you may be happier translating that to sort of averaging a function over the space of all three regular graphs over the finite set. But one thing I want to really emphasize is this sort of input for this primary tool is a simple geodesic, one that does not intersect itself. And so that's very central, that this toolbox is powerful for answering questions about simple geodesics, and can give less information or no information if you are asking about non-simple geodesics. Okay, so this, there's an immense toolbox, started with Mirzakhani's thesis and developed by hers and many others. It's been used for a lot of things, both for the study of Weil-Petersson random surfaces and a huge number of other things. Today, I want to focus on the spectral geometry of the Laplace-Beltrami operator on a hyperbolic surface and its eigenvalues, which are normalized. So this is a version of the adjacency matrix of a random three regular graph or of a three regular graph, but it sort of shifted and normalized. So the eigenvalue of the constant function is 0. And then what I'm calling lambda 1 would be the spectral gap. So you should think of this as a shifted and rescaled version of the adjacency matrix, so that the eigenvalue of the constant function becomes 0. And so this first non-zero eigenvalue, the spectral gap, is of really central importance. It's related to the Cheeger constant. It governs the speed of mixing for Brownian motion and geodesic flow. It governs the error term in what's called the geometric prime number theorem. That's the count of all primitive geodesics on the surface. So this one number controls a lot of things. And so before, there was a meta conjecture that says for every theorem about random graphs, you should try to prove the same theorem for random surfaces. So if one applies that to Friedman's theorem, Alon's second eigenvalue conjecture, which says that the spectral gap for a random graph should typically be as large as possible, the corresponding conjecture for hyperbolic surfaces should say that lambda 1 is typically greater than 1/4 minus epsilon. So when you have a random graph, you compare to its universal cover, the regular tree, and you look at the spectral gap there. When you have a random hyperbolic surface, you look at it, you compare it to its universal cover, the hyperbolic plane. And so 1/4 is the spectral gap of the hyperbolic plane. So this is the exact analog of Alon's second eigenvalue conjecture. And the formal statement would say for all epsilon, the probability that a Weil-Petersson random hyperbolic surface of genus G has lambda 1 less than 1/4 minus epsilon goes to 0 as the genus goes to infinity. So this is the holy grail for a number of people working in the area. I should say very recently. So when I say very recently, I mean since my paper with Lipnowski, there's a beautiful paper of Budzinski, Curie, and Petri that showed that high genus hyperbolic surfaces can never have a very big Cheeger constant. So this, as is the case for graphs, It's not that lambda, the spectral gap is big because of big Cheeger constant. It's just that the spectral gap is large, even though the Cheeger constant is not as large as you might expect looking at the universal cover. So that's a beautiful paper, by the way, that has nothing to do with the Weil-Petersen model. It's for all surfaces, although it uses a probabilistic argument. And I just want to advertise, if you're interested, I recommend looking at it. Okay, so this conjecture is still, you can formulate it in any of the models. It's open in all of the models. And in fact, until very recently, again, since my work with Mike Lipnowski came out, nobody even knew how to make any high genus surfaces with lambda 1 almost a quarter. And so it was only very recently that Hyde and McGee showed there's a sequence of surfaces with lambda 1 approaching a quarter and genus going to infinity. And this resolved the question that had been open since the 80s of just constructing any near optimal spectral expanders in high genus. So that just sort of illustrates the difficulty of the conjecture. Before I go on, maybe now would be a good time to pause and ask for questions again. Are there any questions?
What's the relation between Cheeger constant and lambda 1?
So you have a Cheeger inequality. So the Cheeger constant of the hyperbolic plane is 1. And if it had been the case that the Cheeger constant was typically close to 1, the Cheeger inequality would have proven this conjecture about lambda 1. But Budzinski, Curie, and Petri gave a very precise upper bound that was well below 1. And that's the same thing that happens for random graphs or all graphs. You can't have any large 3 regular graphs whose Cheeger constant is anywhere, or maybe you have to go bigger than 3 regular. But anyways, that whose Cheeger constant is as big as the deregular tree. So somehow Cheeger constant is not quite the right thing. Are there other questions? Okay, so I'll finally tell you what me and Mike Lipnowski proved. So we showed that in the Weil-Petersen model, lambda 1 is typically bigger than 3/16 minus epsilon. So in other words, the probability as genus goes to infinity that a Weil-Petersen random surface has lambda 1 greater than 3/16 minus epsilon goes to 1 for all epsilon. And this is tantalizing. This is, there's also a 3/16 result for, as partial progress towards Selberg's conjecture in analytic number theory. We don't quite know if this is the same 3/16. A different team, Wu and Shui, proved the same result independently and simultaneously. And also a 3/16 result was proven for random covers previously by McGee, Node, and Kuder. All of the recent 3/16 do seem to be the same 3/16. And I should say previously there were other results. For example, Mirzakhani showed in the Weil-Petersen model that Weil-Petersen typically lambda 1 was bigger than something like 0.02, or I forget exactly what her number was. Okay, so 3/16 is smaller than a quarter, so we didn't achieve the holy grail. But this is showing that typically the spectral gap is quite large. Okay, are there any questions about the statement? So I just want to say a little bit about the proof then, which I think is something that will resonate with many of you. So how do you prove bounds on the spectral gap? Well, for graphs, you you do some version of computing the trace of the adjacency matrix, or the trace of a power of adjacency matrix, in two ways. One using eigenvalues and the other one counting loops. So here A is the adjacency matrix of a graph. So we don't have an adjacency matrix, but we have something which is, to my mind at least, is nice, which is the Selberg trace formula, which is a formula that relates eigenvalues of the Laplacian to primitive closed geodesics. So instead of the adjacency matrix, you have sort of an infinite operator. And instead of loops, you're getting primitive closed geodesics. Primitive just means it's not tracing out the same geodesic several times over. And when you think about it, to prove the theorem after a technical examination of the Selberg trace formula, you realize you need to understand the number of geodesics on a genus G surface of length at most some constant times log of genus. And it's enough to do this averaged over the moduli space of genus G. But what I want to emphasize here is you end up caring about all geodesics of length at most a constant times log of the genus, which is a length scale growing with genus. You instantly run into a problem, which is you simply can't exactly compute that, even the Weil-Petersen average. You do have this wonderful toolbox of Mirzakhani, but it only applies to simple geodesics. And again, simple means non-self-intersecting. So not visiting the same part of the surface twice. And certainly lots of geodesics, even of length 5, are not simple. So how are you going to get around this? Well, there's a conjecture that I hope will be natural to many of you, which here I'm calling the birthday paradox conjecture, that says at length scales, so the genus G hyperbolic surface has volume about G, or you should think of it as size G, like roughly G different places you could be on the surface. And so the sort of naive conjecture is that at length scales below square root of the genus, most geodesics are simple and non-separating, but never mind that. And there's a flip side of this too, that if you go above that length scale, they shouldn't be simple anymore. And so this is supported by more sophisticated heuristics, but the easiest heuristic to arrive at this conjecture really has to do with the birthday paradox, right? You think of your length L geodesic as going to roughly L places at random, and you want to know what's the chance it went to the same place twice. And so just the birthday paradox, AKA the probabilistic pigeonhole principle, gives you a guess that's sort of the default guess. So this should be true. We didn't prove it because it was a little bit orthogonal to what we needed, since for us, error terms are central. But what's sort of behind this conjecture is a more detailed picture that says that moderate length scales, like smaller than square root genus, you somehow get the expected number of geodesics on each surface, which is roughly e to the length of the geodesic, but they don't have the expected geometry. If you look at long geodesics on a fixed surface, they tend to intersect themselves a lot, whereas at this length scale, they tend to be simple.
So I have a very basic question about this. So you talk about like counting the number of geodesics on the surface, but aren't there like infinitely many geodesics? Because there's one between any pair of points.
I'm talking about closed geodesics.
Okay, closed. I see.
Yeah.
All right. Thanks.
Yeah. Yeah, that's what, you know, an analogous to computing the trace of the adjacency matrix, there you care about loops. And so maybe it's no surprise that in the Selberg trace formula, you end up with these closed geodesics.
Alex, can I ask about this heuristic of the square root of G length, the birthday paradox? So this is, again, I should just think about this as I'm sort of distributing I think of my square root of G length geodesic as square root of G length 1 pieces, and then I'm throwing them down in these G baskets, these G different places. And that's why it's like the birthday problem of distributing birthdays and, you know, saying that, oh, if I have 20 people in the room, I have a 50% chance of having the same birthday.
Yeah.
Yeah, okay.
Although maybe so you don't feel I've misled you later, I'd say it's slightly better to think of it as like L over log G many pieces, each of length log G or something. The point being that typically you have a spectral gap, and when you have a spectral gap, the mixing of geodesic flow tends to kick in at the log G scale.
Okay.
So in other words, if I look at a closed geodesic and a point on it and a point 1 later, those 2 points are very correlated, of course. But if I look at a point log G later, those 2 points are not very correlated.
Yep. Okay.
So anyways, I hope this will eventually get proved. As I said, it's not quite what we need, because what we care about, the error term is always the most important thing. Anyways, a quick recap. So we want to bound the spectral gap lambda 1 using the trace formula, which is a version of computing the trace of a power of the adjacency matrix in 2 ways. And so we need to know the average number averaged over the space of all hyperbolic surfaces of geodesics of length at most a constant log G. And I want to emphasize for us, it's all about the error term. It's the name of the game is the error term. You could prove the 1/4 result if you could understand the error term well enough. And so Mirzakhani tells us the average number of simple geodesics of this length. And based on that birthday paradox conjecture, we suspect most geodesics of this length are simple. And how do you prove this? Especially, how do you prove this with a very good error term? And so really the central idea that's already present in Mirzakhani-Petri, and of course goes back further than that, is that every closed geodesic is either simple or we say it fills a subsurface. And so a geodesic fills a subsurface if its complement in the subsurface consists of simply connected regions and annular regions about the boundary. So it's sort of like color by number. If you have a geodesic that intersects itself a lot, you find all of the little polygonal, simply connected regions of its complement and you color them in, and maybe you fatten it up a little bit, and that's the subsurface that it fills. And so the central idea is you should keep track of geodesics according to what subsurface they fill. Something really important to remember is a geodesic of logarithmic length scale is way, way, way too small, too short to fill the whole subsurface. And this is a very easy consequence of the isoparametric inequality in the hyperbolic plane. You just apply it to each of the polygonal regions in the complement. So geodesics of this length scale don't have to be simple, but they also can't fill the whole subsurface. So they're of this sort of intermediate complexity. Ideas, computations done by Mirzakhani give bounds for the average number of subsurfaces that a geodesic can fill. So again, this is the key sort of way you do the accounting, the technical estimates, is you think how many subsurfaces, how many geodesics per subsurface. And Mirzakhani, in a sense, has done the work of figuring out how many subsurfaces. And so really what you need to do is figure out how many geodesics per subsurface. And you only have to deal with certain subsurfaces. And so what we do is reduce to what you might call the tangle-free subsurfaces and show that each has very few geodesics. And so I'm drawing an analogy here to the tangle-free condition used in the work of Friedman, where he had to do something extremely similar. He wanted to average the number of loops, or maybe non-backtracking loops or something like that, over the moduli space of graphs. But some graphs had too many loops, were contributing too much to that average. So he called those tangles and he threw them out. So we do something similar. We show that a tangle-free subsurface has very few closed geodesics. And here, tangle-free has a very elegant definition. It just means no pants or one-hole tori with boundary less than some constant. So there's a parameter that's constant in how tangle-free it is. And for typical surfaces of genus G, you can actually take that constant to be astonishingly large, namely log G in size. So you typically only have to deal with subsurfaces that are very untangled, and they don't have many geodesics. So you win. So just a final summary, we're trying to show the spectral gap is big. The trace formula reduces understanding the spectral gap to understanding something about the number of closed geodesics. But you need to think about geodesics at a length scale growing with the genus. And Mirzakhani says there are only so many subsurfaces that each geodesic of this length can fill. And we can show that typically each such subsurface has few geodesics. So we end up mostly caring about the simple geodesics, and Mirzakhani and Petri counted those for us. And so that's the outline of our proof. And I'll say everything is the error term. We did error 1 over the genus, a multiplicative error of 1 over the genus. If you could do 1 over genus to any power, you could put 1/4 here. And I've talked to Joel Friedman about this, and this seems to sort of really align with the story for what happens for random graphs. And so the challenge to getting to 1/4 is to avoid computing all those error terms, but just find some reason they all have to be 0. So just in closing, let me say there's a huge amount to be done in the Weil-Petersen model, which has the benefit of these beautiful recursions. And in all the other models as well. Everything that's known for regular graphs, one can try to prove it for random surfaces. And this might shed light on a lot of different things, including questions in number theory about individual surfaces like the Selberg 1/4 conjecture. So if you're interested in this, and you want a little bit more background, one thing you might be interested in is my survey that's called A Tour Through Mirzakhani's Work on Riemann Surfaces, which appeared in the bulletin of the AMS, that will sort of take you through some of these ideas with the Weil-Petersen measure. Okay, thank you very much.